Thanks for the intro. Yep, so this is joint work with Venkat, and I'll be talking about a new construction of quantum LDPC codes using iterated homological products. So just to give some brief background on what quantum LDPC codes are, these are the quantum analogs of classical LDPC codes. And from a practical perspective, if we have k message qubits or logical qubits, the quantum LDPC code gives us a way of encoding these k qubits into a greater number n of physical qubits, such that even if up to, say, d of these physical qubits are corrupted, we can perform some measurements on these physical qubits in order to recover our original message. And the LDPC condition just means that these measurements are constant weight measurements. So we might measure like the tensor product of Pauli X on these 3 qubits and on these 3 qubits and on various sets of qubits. And the same for some Pauli Z measurements. And we just perform all these constant weight measurements, each just touching a constant number of qubits. And we use these measurement outcomes to recover the original message. And if you're not familiar with kind of quantum computing, these measurements are really the analog of just computing like classical parity checks, just kind of taking the parity of a constant number of bits within your code. So what do we care about? We care about, for a given block length or a given number of physical code qubits, we want to encode as many message qubits as possible. So we want the dimension k of the code to be as large as possible. And we want to be robust against as many errors as possible. So we want the distance d to be as large as possible. And we summarize these parameters by saying the code is an nkd code if it encodes n or k message qubits into n physical qubits with error resilience d. So now I'm going to give like a very abridged history of quantum LDPC code constructions, just to kind of put some context around where a result fits in. This will definitely not be a complete history, but it will have kind of some of the most important results in the context of our work. So the story, for our purposes, starts around 25 years ago, when Kitaev came up with the toric code, which you can think of as the quantum analog, or a quantum analog of the classical repetition code. So it encodes like a constant number of logical qubits into n physical qubits. But unlike the classical repetition code, which is distance n, the toric code only has distance square root of n. And this is really, like, in a very technical sense, it's also an analog of a repetition code, because it's literally just a product of 2 classical repetition codes, where you take this like homological product, which I'll define later. So this was kind of the state-of-the-art construction for a while. But it was kind of generalized by Tillich and Zamor in 2013 to come up with codes that, again, had distance square root of the block length n. But now the dimension of these codes by Tillich and Zamor is linear in the block length. So essentially, they improved kind of from encoding just a single message qubit up to like a linear number of message qubits. And this is, again, taking this, like, using this homological product construction, but now they're taking the product of 2 like asymptotically good classical LDPC codes. So 2 classical LDPC codes where the distance and dimension grow linearly in the block length. And somehow the distance is preserved under this product, or sorry, the dimension is preserved under this product, but the distance takes a square root of n hit, which we'll get into the exact reasons for that later. But kind of this like square root of n loss was ultimately addressed by this beautiful line of work from the past few years, which culminated in a construction of asymptotically good quantum LDPC codes. So codes where the dimension and the distance both grow linearly in the block length. So up to constant factors, these LDPC codes are completely optimal. But they're based on this like balanced or lifted product, which is really like a homological product, but with like some quotienting or some twisting. So it's more of an involved construction. And it's kind of a one-shot thing. You need kind of 2 large, good classical LDPC codes, and then kind of one shot, you take a product of them, you make sure you set things up so that there's a really large symmetry acting on this product, and you quotient out by this symmetry. And so it's a really beautiful construction, but it's also fairly rigid because you need such a large symmetry. And in fact, this is basically the only known construction achieving even close to linear dimension and distance up until this point. Great. So what we're going to describe is like an alternative way to construct quantum LDPC codes where we get almost linear dimension, almost linear distance. But our construction is really different from this balanced product in that we have like inherently iterative construction. So we start with like a constant size object. It'll, in our case, be a constant size quantum locally testable code. And then we iteratively grow this into an asymptotic family. So we repeatedly, starting with this constant size thing, we repeatedly apply a homological product to increase the length, dimension, and the distance, but also to increase the check weight. And that looks something like this. We start with like a given element of our family, and we take a product, and we end up with like a few large blocks of physical qubits, but you can see kind of the number of physical qubits is going to grow, and also the distance and the dimension will grow. But then because the check weight grows from this product, we need to reduce the check weight to get back down to like a constant check weight. So we apply a check weight reduction procedure, which if, for instance, we have this code and there's some like weight 6 check shown here, then we map this to some even longer code, some code even greater number n of physical qubits, but now with maybe only weight 3 checks, so lower weight checks. And by kind of repeating these steps, we can grow to arbitrarily large codes where the distance and dimension are both n to the 1 minus epsilon, and the check weight's a constant. Great. So why are we trying to do this? I guess if we already have these asymptotically good codes, why do we want another construction that parameter-wise isn't even quite as good? I guess the motivation really comes from the success of iterative constructions in classical complexity theory, encoding theory. So I think one of the early examples of this was the construction of explicit spectral expanders from the zigzag product in 2002. And then there's also Deneur's proof of the PCP theorem, Ringgold's proof that ST connectivity is in undirected connectivity is in log space. And kind of maybe most related to our work is actually the construction of classical locally testable codes by taking iterated tensor products by Bensas and Sedan in 2004, and then improved upon by Biedermann in 2015. So we can view our construction as really giving a quantum analog of this construction of classical locally testable codes. Because the quantum setting is in general a bit harder, we're, at least in this talk, I'm mostly going to focus on just the LDPC condition. Local testability, as I'll get into later, is like a strengthening of the LDPC condition. But our results actually do also apply to locally testable codes. So we get like weaker parameters than you get in the classical case. So hopefully it's the motivation that like iterative constructions have been really successful classically. And in some of these cases, like initially the iterative construction just kind of recovered a known result, but in a weaker setting. For instance, like the initial spectral expanders from the zigzag product weren't as good as like Ramanujan graphs. But later these ideas yielded new results. Like they inspired like Ringgold's result and maybe Deneur's PCPs here. So we're kind of hoping for something similar, that maybe if we have iterative constructions, even if they're not quite as good quantitatively for these LDPC codes, they might have like more applications beyond those with current constructions. Great. So I'll now give the classical analog of our result to say show where the motivation comes from and also where the technical challenges lie. And the classical analog is just classical tensor product codes. So if we have two codes, C1 and C2 of length n1 and n2 respectively, we can construct a tensor product code, which is just a code of length n1 times n2. And the code words of this tensor product code, C1 tensor C2, correspond to n1 by n2 matrices, where a given matrix is in the code if every row of this matrix lies in C2 and every column lies in C1. So it's kind of a fairly straightforward construction to define. And this product construction has really, really nice behavior parameter-wise. So if the code C1 has length n1, dimension k1, distance d1, and check weight w1, and then the same for C2, but indexed by 2, then the tensor code is just kind of all of these parameters multiply, and except for the check weight, which we just take a max. So the length is n1, n2, dimension k1, k2, distance d1 times d2, and the check weight is going to be the max of w1, w2. So this kind of behavior is really nice, and it makes it really easy to construct an infinite family of classical LDPC codes by just taking iterated tensor products. So if we just start with some constant-sized classical code, so here n naught is maybe a large constant, and then the dimension and distance we assume to be like n naught to the 1 minus epsilon for an arbitrarily small constant epsilon. Then we can just take this classical code and just repeatedly tensor it with itself. And if we tensor it with itself t times, we get like an n naught to the t, k naught to the t, d naught to the t classical code. But the check weight is still at most n naught, because at each step, we just take the maximum of the check weights of the input codes. So this family will be LDPC and will almost linear dimension and distance. All right, so this is inherently iterative. And Venkatesan and Wiedermann show that this is, in fact, stronger. It's also locally testable. So we're getting something beyond the LDPC property. We're getting this property that if we just choose a random check and use that as like an estimate of kind of how far our given corrupted bit string is from a true code word, kind of the probability that this random check fails will grow almost linearly with the weight of the error. So kind of a random local test, just measuring a random parity check, is indicative of how large or of how corrupted our code word is. So hopefully this just shows that like classical tensor codes behave really nicely, and also it's fairly simple to construct them. So it turns out that when we try to get a quantum analog of this construction, something goes wrong almost immediately. And what goes wrong is that the distances don't necessarily multiply when we tensor. So if we have two quantum codes, Q1 and Q2, we can take a quantum tensor product, or like a homological product of these. I'll define this later. There's a couple of not quite equivalent definitions, but there is kind of a fairly canonical way to define this. And if the initial codes have kind of parameters n1, k1, d1, n2, k2, d2, the product code will have length roughly n1, n2, dimension roughly k1, k2, but the distance a priori could be anywhere between the maximum of d1, d2, and the product of d1, d2. So this is a really large gap. It's like a quadratically large gap if d1, d2 are roughly the same. And classically, as we saw, kind of we're always at this upper bound of d1 times d2. So kind of you can view the main purpose of this talk as characterizing, giving kind of sufficient conditions for when we can recover this upper bound of d1 times d2, when we can actually show that this upper bound is roughly tight. And you can kind of view this challenge of like, when do the distances multiply? That's actually one of the central issues in quantum coding theory as a whole, because it was a really long-standing open question to get quantum LDPC codes of distance beyond this like square root n barrier. It was only like in around 2019 or 2020 that the first examples with distance like significantly above square root n were constructed. Whereas classically, this kind of tensor construction like immediately gives almost linear distance. So the fact that it doesn't easily work quantumly has really been one of the big challenges in quantum coding theory. Great. So I'll now state our main technical result, which is the sufficient condition for these distances to multiply. So if we have two quantum codes, Q1, Q2, we consider the product. If we assume that Q1 has check weight W1, we assume that Q2 is locally testable with soundness ρ2. I haven't defined soundness here, but here, just think of like maybe ρ2 being a constant. So this is like a good locally testable code. Kind of a random check is highly indicative of how large the error is. Then our product code has distance growing as d1 times d2 divided by w1 over ρ2 times this additional parameter n2 prime over d2 prime, which is kind of the length and distance of some code closely related to the code Q2. So if we imagine like w1 and ρ2 are constants, so we start out with really good codes. And we can also assume like n2 prime over d2 prime is roughly a constant. If this code closely associated to Q2 is also a good code, then essentially we're recovering almost the linear scaling of D with D1 times D2 that we had in the classical case. So at a high level, the takeaway here is kind of if our two starting codes are LDPC, they have low weight checks, and one of them is locally testable, then all of a sudden we can ensure that the product of these two quantum codes gives another quantum code with distance scaling as the product of the distances of the input codes. Right. So I'll now just briefly give a couple more details on how we apply this in our iterative construction. Then I'll try to explain the intuition for why this result is true. So as I mentioned before, we start with just a constant size quantum locally testable code with like check weight much less than the block length and soundness kind of fairly close to a constant. Or I guess n naught here is a constant. So really both of these are constants. Then iteratively, we just start with kind of Q naught and we construct each member of family Qi plus 1 from the previous member Qi by just kind of taking the product with our starting code Q naught. This will kind of multiply the length, the dimension, the distance by kind of n naught or n naught to the 1 minus epsilon. So it'll increase all three parameters, but it will roughly double the check weight. And then we just apply this known check weight reduction procedure by Hastings from a couple of years ago, which can reduce the check weight back from 2W naught down to W naught. And when we repeat, we get our infinite family of almost linear distance and dimension quantum LDPC codes. Great. So I'll now try to give some intuition for this technical result, this key condition I mentioned, where if the starting codes are LDPC and one is locally testable, then we get the distances multiplying. And to do this, I'll need to introduce a bit of machinery around chain complexes. So it's really helpful to view quantum codes as these chain complexes, which are simply sequences of vector spaces over a finite field in our case, connected by boundary maps, with the key condition that if we multiply together two consecutive boundary maps, we get 0. So each like delta I here is a boundary map. So then the quantum code, so a quantum code in general, we can think of as a pair of classical codes. Intuitively, kind of the thing that makes a quantum code quantum is it has to protect against errors or bit flips in two different bases at the same time, an X basis and a Z basis. So we can think of a quantum code as kind of a pair of classical codes that interact nicely so that the kind of error correction in the X basis and the Z basis don't interfere with each other. And specifically, this condition that they don't interfere with each other is just the condition that we want our two classical codes to each contain the dual of the other code. And you can see that this condition that in a chain complex that the product of any two consecutive boundary maps is 0 precisely means that if we take kind of one code to be one of our codes to be the kernel of the transpose of the boundary map at level I plus 1, and we take the other code to be the kernel of the boundary map at level I, then these two codes will each contain the dual of the other precisely because the boundary maps at level I and I plus 1 multiply to 0. So we can define a quantum code at every level I of the chain complex. And it has length ni. Its dimension is the dimension of qz minus the dimension of qx perp. And its distance is this expression here. And really, we should be thinking of this quantum code as kind of like a coset code, or the kind of, we should associate the quantum code with the quotient space qz mod qx perp, or like the kernel of delta I modulo the image of delta I plus 1. You can see kind of the dimension of the code is literally like the dimension of this quotient space qz mod qx perp. And the distance is the minimum weight of any non-zero representative, or the minimum weight of any representative of a non-zero coset, and qz mod qx perp, or in qx mod qz perp. And the check weight is just kind of, we think of these boundary maps as like parity check matrices, so the check weight is just the minimum Hamming weight of any non-zero row or column in any of these matrices. And we can kind of view a classical LDPC code as a chain complex where it's just kind of a two-term chain complex, where kind of if there's n1 bits and n0 checks, then the chain complex is just this map from fq to the n1 to fq to the n0, where the boundary map is literally just our parity check matrix. So classical codes are like two-term chain complexes. Quantum codes require at least 3 terms in the chain complex. Right, so how do we take products of quantum codes or products of chain complexes? I'll kind of describe this through examples to try to kind of draw it out, and also illustrate why it's difficult to ensure that the distances multiply when we take these products. So maybe the first time this was like systematically done was by Tillich and Zamor in 2013, and this result I mentioned at the start, where they constructed these quantum codes with linear dimension, but square root n square root of the length distance by taking the product of 2 classical LDPC codes. And the way they take this product is they take the chain complex associated to 2 classical LDPC codes. So here A and B are these two-term chain complexes. So the boundary map here and the boundary map here are just the 2 parity check matrices for your 2 respective classical LDPC codes. So like code words live within like A1 or within B1. So A1, A0, B1, B0 are all vector spaces here. And then the product chain complex we get from this picture, where we essentially take a grid where we tensor either of these vector spaces with either of these vector spaces. So we get 4 tensor product spaces, which are like spaces of matrices. And then we have a bunch of maps going between them, where each vertical map simply applies the boundary map from A to every column of these matrices, while the horizontal map here simply applies the boundary map or the parity check matrix from B to each row of a matrix in this space. And then we get a quantum code by placing our qubits along the diagonal. So we have kind of two grids of qubits. We have one grid up here of qubits and one grid down here of qubits. And then we have one grid of kind of x checks corresponding to this space, and we have one grid of z checks corresponding to this space. So this is maybe a bit abstract, but just from this picture, we can already get an intuitive idea for why the distance will only grow as n instead of n squared, assuming that both of the classical LDPC codes A and B have length n. And the reason is that each qubit in this picture, in both the x and the z basis, is only protected by one of the 2 parity check matrices, either from the code A or from the code B at a time. So for instance, if we look at a qubit kind of up in this grid here, we see that it's protected by this vertical map. So it's protected by the parity check matrix from A, but there's kind of nothing coming out to the right. We can imagine there's just like the 0 map coming out to the right. So there's kind of no non-trivial parity check matrix protecting qubits up here in the horizontal direction. And similarly, we have something similar going on down here, but in the vertical direction. So we can really think of intuitively, like with this product code, we're kind of getting the behavior of a classical tensor code, but where one of the 2 codes has parity check matrix 0, or it's like the code is the entire vector space, so it is distance 1. So intuitively, this quantum product construction we've drawn is kind of like a classical product of like a good code with a trivial code. And intuitively, that's why we're only getting like we're only getting distance from one of the 2 inputs. So our distance will grow as the square root of the final block length. Great. So in this work, like our key idea is to find a way to improve upon this, kind of circumvent the square root n barrier, and actually get the distance growing as the product of the 2 distances. And the way we're going to do that is just to take longer chain complexes. So we're now going to start with not classical LDPC codes, but we're going to start with quantum LDPC codes, A and B. We'll actually take A to be a 3-term chain complex and B to be a 5-term chain complex. And then we'll take the product, so it's this huge messy picture, and we'll place qubits across the middle diagonal, x checks on this diagonal 1 to the left, and z checks on this diagonal 1 to the right. And the key idea now is if you look at qubits in this middle region, like at the very middle, A1 tensor B2, there's now like non-trivial boundary maps going in all 4 directions. So in both the x direction up here and in the z direction down here, kind of qubits in this region are at least intuitively speaking, they're protected both horizontally and vertically. So we have kind of it seems like we have kind of a good tensor product structure around these qubits. So we could hope for linear distance for qubits inside here. Indeed, we show that that's the case, assuming that like this code A is LDPC and this code B is locally testable. And the proof is kind of inspired by a relayed result by Kaufman and Tesler from a few years ago, where they did this, but they kind of did a one-side picture. They were trying to like just get z distance, but not also x distance. But yeah, kind of using local testability, which is kind of a form of expansion, we can argue we end up just kind of doing some snake-like argument. We kind of trace through this diagram and argue that using this local testability, we must have good distance for qubits in this middle region. So I guess that was kind of a sketchy argument, but hopefully it's at least given some intuition about and where this result is coming from. So just to wrap up, so we obtain an almost good family of quantum LDPC codes, meaning the dimension distance grow almost linearly in the block length, using iterated products and weight reduction, starting from a constant size quantum locally testable code. Whereas all prior constructions with similar parameters use this kind of one-shot balanced product construction. So just to highlight some open questions, maybe the most pressing one from our work is kind of how to find alternative ways to construct this constant size quantum locally testable code. Because unfortunately, the only known current constructions are actually themselves use this balanced product construction. So currently, the only way we know how to instantiate our construction is to take a constant size balanced product, to construct a constant size quantum locally testable code, and then create an infinite family by iterated tensor products. So it'd be really nice if we had other ways to construct like a constant size starting object. So then we'd have like an end-to-end construction without this balanced product at all. Then there's another question, which is like, can we get new applications of our construction, maybe that go beyond things you can do with these other balanced product constructions? It seems like perhaps there's some applications to fault tolerance, like performing fault tolerant computation on the messages underlying these code words, but it would also be cool to get additional applications. And there's also just the question of getting additional types of constructions. So we've given like one new type of construction on top of the existing ones, but maybe there's also totally other ways to get new families of good quantum LDPC codes with interesting properties. So thank you.